When you look at your smartphone, it's like magic, right? You've got these super complex apps, you're streaming video, you're connected to the entire world. But what if I told you that all of that, every single bit of it, is built on a foundation of these simplest decisions you can possibly imagine? I'm talking on or off, yes or no. Today, we're going to pull back that curtain and meet the tiny little decision makers that run our entire digital world, logic gates. So here's the game plan. We're going to start at the very beginning with the world of ones and zeros. Then we'll meet the basic toolkit, the fundamental gates. After that, we'll see how you can combine them to get some real power, learn the simple language circuits speak, and then we'll finish up with a concept that is, frankly, mind-blowing, the one gate that can build literally everything else. Okay, first things first. Every single piece of information inside a computer, your photos, your music, every instruction, it all gets broken down into the simplest language possible. A language that only has two words, on, which we call a 1, and off, which we call a 0. That's it. This is the binary system, and it is the absolute bedrock of everything we're about to talk about. So how do you actually do anything with just ones and zeros? Well, that's where these little guys come in. Think of a logic gate as a microscopic bouncer at a nightclub. It looks at who's trying to get in, those are the inputs, and based on a single super simple rule, it decides who gets through. That's the one single output. They are the fundamental building blocks of, well, everything digital. All right, it's time to meet the team. Now, there are a bunch of different logic gates, but they're all really just combinations of three super simple fundamental ones. You can think of them like primary colors. With just these three, and, or, and not, you can build anything. So let's get to know them. First up, we've got the AND gate. This one is the strict one. It's the tough gatekeeper. Imagine a vault door that needs two keys, key A and key B turned at the same time. If you only have one key or you have no keys, that door is staying shut. You get nothing. The output is a 1 only if input A and input B are both 1. And this little chart, it's called a truth table, shows you every single possibility. Look at it, see? There's only one single row where the output, Q, is a 1, and that's when both A and B are 1. Any other combination, you get a 0. Simple as that. Next up, we have the OR gate. Now this one is way more laid back. It's a merging function. Think of it like a door with two different keyholes. If you have key A or you have key B, you can open it. You don't need both. So it's way easier to get a 1 out of this gate. As long as any input is a 1, the output will be a 1. And you can see that reflected in its truth table. It's pretty much the total opposite of the AND gate. The only way you can possibly get a 0 is if both inputs are 0. If A is 1, or B is 1, or even if both are 1, the output is always 1. And finally, the last of our primary three is the NOT gate. Some people call it an inverter. It's the simplest one of all, but it is so important. It has just one job, to do the opposite. It takes one input and just flips it. A 1 comes in, a 0 goes out. A 0 comes in, a 1 goes out. That's literally the whole story. I mean, look at its truth table. It couldn't be simpler. 0 becomes 1, 1 becomes 0. It's a simple flip, but this ability to invert a signal is absolutely critical for building complex logic. Okay, so we've got our basic toolkit, AND, OR, and NOT. But this is where the real fun begins, because the true power isn't in using them alone, it's in combining them. By snapping these simple gates together, we can build brand new tools with much more advanced and useful functions. So check this out. This is a NAND gate. The name pretty much gives it away, right? It's a NOT AND. All you're doing is taking the output from an AND gate and then immediately flipping it with a NOT gate. And the result? It's the exact opposite of the AND gate we saw before. The only way to get a 0 out of a NAND gate is if both inputs are 1. And you can probably guess what's next. The NOR gate. Not OR. Same idea. You take the output of our friendly, relaxed OR gate and you invert it. So now, the only possible way a NOR gate can spit out a 1 is if both of its inputs are 0. It's the complete inverse of the OR gate. Now for a really cool one. This is the XOR gate, which stands for exclusive OR. This gate answers a very specific question. Are the inputs different from each other? If they are different, it gives you a 1. If they're the same, it gives you a 0. You know the perfect analogy? A light switch at two ends of a hallway. The light state flips only when the two switches are in different positions. That's XOR logic. So let's just make this crystal clear. A regular OR gate is happy if both inputs are 1. It gives you a 1. But the exclusive OR gate says, nope, not good enough. In that case, it outputs a 0. It's all about exclusivity, one or the other, but not both. And this function is ridiculously important for things like comparing values and doing basic math inside a computer chip. So you can imagine trying to design a processor with millions or even billions of these gates. You just can't draw that out. It's impossible. So engineers needed a language, a shorthand to describe all this logic on paper. And that solution is called Boolean algebra. Now, don't let the word algebra scare you. It's not complex math. Just think of it as a simple, powerful language for writing down circuit recipes. And the symbols are super easy. A little dot, like a multiplication sign, means and. A plus sign means or. And if you see a bar over a letter, that just means not. You invert whatever that value is. And just like that, we can write out these complex logic functions without drawing a single thing. And just like the math you learned in school, there's an order of operations so that everyone's on the same page. It's kind of like PEMDAS. You always handle the nots first, then anything inside parentheses, then all the ands, and finally, you do all the ors. It's a system to keep things from getting messy. So we've met our basic gates, we've seen how to combine them, and we know we can build all sorts of complex things from our toolkit of and, or, and not. But this leads to a really wild question. Could we make our toolkit even smaller? Seriously, just think about that for a second. Could you build an entire computer with all of its insane complexity by just using one single type of gate over and over and over again? I mean, that sounds completely impossible, right? Well, the answer is yes, absolutely. And the magic component that can do it all is that NAND gate we met a little while ago. Turns out, the NAND gate is what we call a universal gate. Because by arranging NAND gates in clever ways, you can perfectly create a NOT gate, you can create an AND gate, and you can create an OR gate. And if you can build those three, you can build anything. This quote just says it all perfectly. The truly profound idea here is that the absolutely staggering complexity of a modern computer processor is, when you get right down to it, built from the endless repetition of one single, very simple logical rule. That's an incredible, powerful idea. So let's just recap the whole journey real quick. All digital stuff is just ones and zeros. Simple gates like and, or, and not are the basic tools that make decisions. When you combine those gates, you get more complex functions. And amazingly, a single universal gate, our hero, the NAND gate, is all you really need to build any digital system you can possibly imagine. And that kind of leaves us with one last big thought to chew on. We've just seen how mind-boggling complexity can just emerge from one simple rule repeated millions of times. It really makes you wonder, doesn't it? From the patterns in a seashell to the way a city grows, what other incredibly complex systems out there in the world are maybe, just maybe, built on a ridiculously simple foundation